Hi and welcome everyone. I'm Tim Moreton. I'm founder and CTO at Acunu. I will tell you a little bit about the background of Acunu. So we started out building a storage engine. In fact, a storage system for virtual machine environments. So looking at block storage. And this was sort of 2009, 2010. And we recognized that sort of pretty soon after that, we got some great technology. It all worked quite nicely, but we recognized that there wasn't really a market for the sort of ability to manage large volumes of structured data in the context of a block environment. You know, at the one end you had sort of EBS, and at the other hand you had EMC, and there wasn't really a middle there. So we thought, hey, what should we do with this cool technology we've built, you know, like every startup does? And we plugged it into the set of sort of distributed databases that were coming onto the market at the time. And one of them that we really liked the look of and that seemed to work pretty well, especially compared to the other ones at the time, was Cassandra. So we sort of offered Cassandra with this storage engine for a little while, and that was all going well, but we sort of really observed that one of the challenges that people had around using Cassandra was how do you build analytical applications on top of it. So, you know, Cassandra, a lot of the use cases that we were seeing were people trying to get back, I guess, the sort of rich query semantics and framework that people were familiar with and coming from a relational background. So that's, I guess, the genesis of Acunu Analytics. So I'll tell you a little bit about that, and then go on and maybe show it to you if the wind is coming from the right direction and so on. So I guess the first thing is, like, analytics on NoSQL, does it even make sense? Why would you not just use Hadoop? And I guess the sort of answer to that is that, well, you should use Hadoop. You should use Hadoop for the sort of analytics where you don't really have a good idea about the question you're trying to address in advance, and where you're trying to tackle data sets with a large amount of variety and not very much structure. And that is really a perfect fit for the world of Hadoop. And indeed, Hadoop has really taken over from or supplemented the traditional world of data warehousing because it allows you to deal better with data sets which are unstructured. So if you're trying to find the unknown unknowns, or the sort of so-called needles in a haystack to help you inform some business process 6 months down the line, you're really interested in how meteorological data is going to affect your widget sales, and you need to tell your sales force to do something subtly different and send a memo out at the end of the week, then Hadoop is a great fit for being able to tackle those sorts of problems. And I sort of call that discovery analytics. It's data mining, doing a bit of complex machine learning, and generally trying to do arbitrary computation on very large unstructured data sets. On the other side of the spectrum, and this is, I think, where NoSQL and general, and I think Cassandra in particular, are a much better fit, and where there are many more sort of use cases and case studies of people doing this sort of thing, is around what I would describe as operational intelligence. So here, you're not trying to find the needle in a haystack. You probably already know what the metrics are that matter to you in advance. So perhaps you're monitoring a whole huge cluster of servers, and it doesn't take a Hadoop cluster to tell you that looking at your 95th percentile latency of API calls or looking at load average is a metric that should matter to you. If you're in advertising, looking at click-through rate is clearly a metric that matters to you. You know that from your own domain knowledge, right? And so operational intelligence, I guess, is about being able to build dashboards and build systems which react to changes or potential problems in those metrics, rather than sort of discovering new metrics in their entirety. So, and in particular, often that contains a sort of real-time element. So, in particular, you're looking at sort of use cases where 5 minutes matters. If there's a business decision you could make better on the back of fresh data, or if there is, I guess, something you can do to sort of raise the alert, raise the alarm, and go and fix something because you've spotted that it's broken, or because something's gone wonky, or even better, do it predictively before something goes out of band or out of bounds, then that's great. Cassandra is a great platform for doing that sort of analytics on. And here you're really dealing much more with velocity rather than variety. Volume just sort of these days tends to feature all over the place. So you know, we've been contributing to Cassandra for a long time, and we've been using it, and like it's great to see you know its continued adoption. It has some great properties. So in particular, it's highly scalable. You can just add machines and increase capacity, increase performance, and the multi-master architecture that Cassandra has means that it doesn't create you operational headaches as you grow it. It's very, very fast. In particular, it's very fast for writes. And that's really useful when you're doing operational analytics, because what you tend to do there is you're collecting this big stream of data, or perhaps you're collecting or trying to record information, perhaps you're counting stuff about this big stream of data, and you're potentially reading it back, showing it on a dashboard or raising alerts much less frequently. So your write rate to read ratio is often like 100 or 1,000 to 1. That's typical for the sort of customers that we work with. So the fact that Cassandra is very, very good at writing fast is important. It's also highly available. I think it's one of the only stores out there where within sort of 10 minutes you can set up a cluster and tell it to span 3 data centers, and it'll just do it in a sensible way. And that's a really useful thing if what you're looking to do is make sure the system is always on to be able to collect data, or always on to be able to serve those results. So it is dependable. It's not always been dependable since back in the days of 0.5 and 0.6. But what's really pleasing to me is that there are many what I would class as sort of risk-averse organizations who are beginning to deploy Cassandra in mission-critical settings, and it has really hit the mainstream in that sense. And it also has atomic counters, which are the building block of analytics. Being able to basically throw +1s at the store allows you to build graphs and quantitative analytic applications on top of Cassandra. So all of that's great, right? So there's always still a challenge though, because NoSQL giveth and NoSQL taketh away. So this cartoon was not about Cassandra, obviously. Cassandra doesn't really need you to write distributed MapReduce functions in Erlang, but the point still stands, right? Not wanting to poke too much fun at our friends over in the React world, actually, it is still pretty hard to query Cassandra. So, you put your data in, and then you have to pull it out roughly in the same way that you put it in. And the sort of whole process of denormalizing your data, which Cassandra encourages, means that you need to think in advance about how you want to read data out of Cassandra. And that's fine, unless you get into the situation as Bob and his mate do here. Is mate a Britishism? I think it might be. Anyway, Bob and his mate have got into the situation where Bob wants to query the database himself, right? In fact, there's a middle step, right, which is that you build this great application and then the requirements change, and you then have to query it in some other way, and you have to change your Cassandra data model to adapt to that, and that's a real pain. And in particular, if you then need to roll that back over historical data, that's really hard as well, because you have to probably write scripts, or you have to munge it in some way. And then the step beyond that is when Bob wants to be able to ask queries himself and has to become an expert in Cassandra data modeling, which is getting considerably easier with the advent and improvements in CQL3, but it still ain't at the position, and I don't think it ever has really intended to be, where you can just give it to a business user and let them loose on it. So we wanted to change some of that, and working with a number of customers, as I was saying earlier, who were just starting out with Cassandra, data modeling, and particularly data modeling for analytical applications, was certainly the hardest problem that they were encountering. So we built this thing called Acunu, and I'll dive into a bit of technical detail about it in a sec. But basically, you take events, So we have a HTTP API where you can just throw JSON at it. We have Flume integration, Kafka integration, and a range of other things now. And basically, it just sort of does your data modeling for you. You describe tables and sort of dimensions, like the sort of fields that correspond to the keys in your JSON objects, say, and say this is a time, or this is a path, like a sort of hierarchical structure, or it's a number. And we basically turn those tables and sort of the templates of the queries that you want to ask on them into operations on Cassandra. So an event turns into writes on Cassandra, and we use Cassandra to store both the raw events and these intermediate results as well. And the reason we do that is because we then allow you to ask queries of it in a rich SQL-like language, and we decompose those queries into reads on the sort of data model in this materialized view we've built. So you can think of this as basically like OLAP on top of NoSQL. So we let you build OLAP cubes and update them in a continuous fashion. And rather than you coming back to your data warehouse the next morning and getting the results from yesterday and getting a sort of cubing environment set up from yesterday where you can sort of slice and dice your data, actually that just happens continuously. And we can do that because of the great features that Cassandra has. And on top of that, we've also built a bunch of dashboards, so like a browser-based set of dashboards I'll show you to sort of help you visualize all this stuff in real time. So how does this work? So the first step is that you define aggregate cubes. This is sort of logical progression, right? So you say, we keep the spirit of denormalization that Cassandra has, and we basically ask you to say, tell us how you're going to be querying your data, but in a sort of much more sort of templatized sense. So a cube consists of an aggregate function, something you want to do with the data, and a set of dimensions that you might want in a where or a group by clause. So here we're going to build a cube which takes the approx top 5 or 10 or whatever keywords, and we are going to want to be able to specify and filter by browser and by time, and then we want to be able to group by time buckets at a sort of granularity there. So what happens is as we collect these events, we do the work to update all of the potential places in the materialized view that that event features. So for example, if you're counting by day or counting by hour of day or counting uniques by hash tag or something like that, and the event features in a range of different places in these cubes, we will convert that single event into multiple writes, which is fine because Cassandra has great write performance. We also stored the raw events as well. I'll come back to why in a sec. But when you ask a query in the Acunu query language, which looks, as you can see, cunningly like SQL, you basically, what we're doing there is just decomposing that into reads, basically get slices in Cassandra on these cubes. And I guess the benefit of doing that, the key observation here is that we're never having to touch that original data if you're going to ask a query. So if you go into Hive and you do select count from your whole data set, that's going to take a while because it's got to go over every record and it's going to have to pull all of that back. So the whole purpose here is that by you guys specifying the sort of shape of queries that you want to build in advance, we can do the work as events come in so that you can get instant answers. That's the basic idea. But we do maintain mappings to the raw events as well. So if you spot a particular outlier in your latency distribution and you want to drill into that and find out particularly why that's occurred, you can still see the raw events through that. And of course, then when your boss comes and changes their mind about the requirements and says, it would be great if we could have this different cube, or if we could group by this other dimension, or could you show me this other dashboard? We allow you to, oh, and by the way, I want results for yesterday as well, because I want to compare them. We allow you to take the raw events, we diff the schemas, work out the underlying data that we need to change in order to be able to get that historical data, and backfill. We basically backfill by pumping those raw events into the new cubes. Does that make sense? Cool. So, okay, let's do a concrete example. So, basically, imagine you've got some data like this. So we break, every cube is represented in Cassandra by, not every cube, I guess a table will be broken down into a set of column families in Cassandra. So under the hood, we are maintaining a set of materialized views. So each cube is basically a materialized view. And the basic way of thinking about it is a where in your cube is a projection onto a particular row, and a group by, roughly, is a set of columns within that row. And for each sort of set of hierarchical aggregates, say you want to be able to count by hour and you also want to be able to count by minute, each of those represents a sort of a step of a group in your columns and a set of rows as well. So here, for example, just to sort of understand that, right, what you want to be doing is, when I say something like select count where time is within an hour and group by minute, I want to be able to do as little work in Cassandra as possible to pull that data out. So the way we organize that is to have the hour as the row key there, and to be able to have the minute as the column key. So a single get slice operation in pre-CQL3 terms allows you to get that answer. And of course, the original event has to update a whole bunch of different counters. So just talking about counts here for now. And likewise, if I want to do something like where geography equals US group by user, the user features in the group by in the column key, and the row key is US. And of course, you can see that you can end up, if you've got multiple columns, multiple dimensions in your where clause, you can end up with sort of compounded row keys. So that's the sort of very basic example. So there's a number of other things that you can do with this. So we support hierarchical aggregation as well. So you can break URLs or paths of something like data center /rack/machine down. We support arithmetic expressions, limits. You can do filtering at query time. We deal with time zones. So if you are inserting events with a whole range of different time zones, and then you want to come back and query 10 o'clock, 10:03 Pacific through to 11:57 UTC, we'll piece together the buckets that are available with a minimum amount of effort and just return you the overall results. And then you can do inner and outer joins. That warning, that happens at query time. It's designed as a convenience thing for you to do on sort of low cardinality dimensions. It's not designed to replace sort of massive inter-machine joins in a data warehousing context. So, and then you can do sort of SQL subquery type things, but I personally can't get my head around SQL subqueries, so I think a pipe for syntax is much easier to think about, where you can take the result of one query on a cube and then ungroup or regroup or summarize by something else. So in that example, doing sum of a particular value, sum and counting from V group by category, and then basically taking the sum of S and sum of C as the actual average of those separate aggregates. So far, like, I guess what we've been talking about is really making ingest simpler, giving you a HTTP JSON based API, making queries richer, making the process of denormalization a bit less painful, but still giving you some of the benefits of it and giving you some visualizations. If you see what you have here, it's basically still a tool for developers. So if you look at this sort of workflow of install, create tables, define cubes, like plug in your data feed and then build widgets, well, only the widget building bit is really doable by Bob, right? Everything else, Bob is sort of still has to go and pester this other guy for. So one of the things we wanted to do was change that a little bit. So we released Analytics v5 last week, and one of the things so Bob still has to, the other guy has to still install it. But one of the things we did there was really try and improve the workflow for business users. So try and give you the equivalent of one of the rich BI tools that you've had for years in SQL in the world of NoSQL, in particular and only on Cassandra. So we now allow business people, as I'll sort of demonstrate, to basically create schemas by having the equivalent of sort of an automatic import wizard that looks very similar to the one that you'll find in Excel. We allow them business guys to build widgets by adding a sort of drag and drop UI, which sort of does an ad hoc query and then works out what cubes you need to fulfill that, creates those cubes, backfills them, and then updates for real-time data, of course, as it comes in. You still need to get this other guy back involved when you turn on the data feed, but that's getting a bit easier. We've built a set of ingesters and other sort of add-ons so that you can just from the command line plug in different data sets, and that's definitely getting easier. And then you can that your developer then can get out of the picture and get on with more useful stuff, and you can leave Bob to go and iterate on the analytics and dashboards that he's been building. So okay, you guys will see that. So I'm going to start with a fresh analytics instance here, and what I'm going to do is just upload a file that we prepared earlier of slightly munged tweets. So I'll show you what they look like. So they're basically just JSON events, right? So they're JSON objects with like keys and values inside them. In fact, the keywords here have been split out, so maybe we're cheating a little bit, but you basically just give it a set of events, and we will then look at those events and work out what the structure of them is. So we sort of correctly infer that timestamp is a time. We completely incorrectly infer that keywords is a path. So we also support this type bag, which is a bit like a set of tags. So if you send an event with a sort of an array of strings in it, we'll sort of process those and pull them out as a bag. What have we got over here? User, country, string. Great. That's good. Tweets, path. Yeah, that's wrong. It should be a string. So I don't really need to know very much about cubes or analytics to be sort of doing this. The sort of target audience is somebody who can use a pivot table in Excel. So I've just created my enormous big data set of 40 tweets from my file, and now want to do some big data analytics on all 40 of those tweets. I think there were 40 in there anyway. So I can drag count up here. Yeah, 40. And I could. This is just doing an ad hoc query from the raw events at the moment. So there's no cubes here at all. And so let's group by country, shall we? So I group by country. I get a picture which breaks that count down by country. I could turn it into a map if I can find the map. There we go. And at this point, maybe I'm happy with it. So you can see underneath, by the way, that there's a query that's going on here. So we do an event store query, we pipe it through, and we sort of do a fake cube query. And by the way, for every query in here, you just have the set. All the UI is doing is just using our HTTP API, which is available to your applications, and we'll just give you JSON back. Yes.
Okay, so you load a flat file, right?
Yeah.
If you actually want to have cubes, do they need to be pre-created in these files, or somehow Acunu may figure it out later? You just load flat files and create cubes later.
Yeah, so that's what's happening here. So I've just uploaded a file, and there's no cubes in here yet.
Okay.
So this is just if you watch, when I click add to dashboard here, basically this is the cube I need, right? I need to count from tweets group by country, but I'm missing that cube. So new cubes will be created to support instant updates as widget. So when I click add widget, that cube will be created, and with that tick box field, it will populate it with my vast amount of historic data. So if I refresh that, yeah, there we go. So now it's on a dashboard, and I can drop down to pull in some Twitter data. We put together this Twitter ingester, which I will attempt to start. grab the... So we have this plugin framework now for ingesters where you can basically write your own or download off GitHub different types of ways of getting data into Acunu. So you have this notion of an ingester and then a flow. So a flow basically takes data of a particular sort and pipes it through to a table in analytics. So the table that got created, I'll just go and show you that. The table that got created was basically had these fields that we created, and it's now got one cube in it. So when I go through and create that flow, fingers crossed, it'll go to Twitter and pull us in some events. Although it did try and rate limit my API key earlier, so there's no guarantee that that's going to happen. Oh, there we go, we've got some. Okay, so if we go back to the dashboard we just made, you know what? So I can change the visualizations on it later as well. So change to a pie chart. If I make that live, let's see what happens. Hooray! So we're getting some Twitter data about countries. And then talking about drilling down to raw events, if I can click Canada here, you can see the tweets that were coming in from Canada. Yeah, country Canada. So that's basically it. And I didn't really need to understand anything about a cube before creating those visualizations, which makes things an awful lot simpler. And all of this is powered by Cassandra, and we are doing this across a range of verticals, from like web and visitor analytics through to financial market data analytics at investment banks and Internet of Things. And it's just trying to make rich queries on Cassandra a sort of a step easier. Okay, thank you. Any questions?
How do you actually license this?
How do we
License.
it? So, so analytics itself is closed source. Everything we do at the Cassandra layer, we push back into the community. But analytics itself is closed source. It's a sort of annual subscription basis. I can chat to you more about details after.
How do you do the Cassandra data modeling?
Sorry?
How do you do the Cassandra data modeling?
How do we do it? So, so by taking the definitions of the cubes that you set up, we work out what we're going to need to insert in rows and what we're going to need to insert in columns, and build a data model that maps that. So under the hood, we're creating, we create a key space used by default called analytics, and then we create column families within that which match the cubes that you set up. And then we have to do, because Cassandra's got some limitations on your ability to change the schema after the fact, we sort of have to do a bit of funky serialization of our own to sort of make that work. So say you want to change a field which you first declare as a number into a string, and then you want to create a different cube on it. So we at that point we end up having to do a bunch of our own serialization. But more or less all we're doing is mapping sort of higher level constructs about, like, I want to query this data with this in the where clause and this in the group by clause onto a set of data models, basically a set of constructs in Cassandra for you.
What happens over a period of time when my event definitions also change?
So what happens if your event definitions change? Well, you can go and change these things if you like. So for example, I can add a field, so I can go and change that, and I can add a new field. If I've already been collecting events with that field, that's absolutely fine. We'll have been storing those events, and then you can come and backfill them and pick up that data from those events you've already collected. So yeah, you can change the structure as you go, either by adding new fields, dropping cubes, or changing cubes. So it's just to try and make the whole changing of requirements process a bit simpler.
When you change the schema, does it create another cube, or does it reprocess from the raw?
So when you change the schema, so in terms of adding a new cube, yes.
Asking a different question.
Right. So yeah, so I add a new, say I want to do something like, I want to do approx count distinct of keywords, and I want to be able to group that by country. when I click Add Cube, I'll create a cube, and that will build a set of new, potentially a new column family, but certainly a new way of storing data within potentially existing column families in Cassandra. And it won't touch any of the raw events unless you click this button here which says backfill. So at that point, we will then take a slice of data from the past and basically do this distributed process where we roll over the raw events and pull them back into this new cube so you can get historical context. But if you don't care about history on this new cube, you don't have to do that. Obviously, that's a bit like a MapReduce. It takes a while.
Yeah, I get that. So if I have an operational dashboard and it has, I don't know, 7 graphs on it, do I have potentially up to 7 different cubes? Or?
Yeah. Yeah. If the graphs are showing different things, so you might have graphs which are showing, clicks from people in California, clicks from people in Oregon, and maybe they're the same cube but just with different parameters filled in. So a cube represents like a sort of unparameterized shape of query.
Okay, got it.
So what is like data storage overhead? If I have a terabyte of flat files, how much space it will take in Cassandra?
Right, so you're right. So there is definitely a space blow up by maintaining materialized views. So I mean, the question, so just for the recording, the question was, what's the space blow up if you've got a terabyte of data? However, Cassandra has built-in compression, which is actually really, really good. And also, all we're doing is just, for most of these things, is counting. So numbers don't really take up a lot of space. It's actually the keys that are the large element. So we do have some data structures which aren't counts, like so we support a prox count distinct, for example, which uses a sort of probabilistic sketch algorithm to give you a better performance on count distinct, which is quite hard to do. And there, the sort of space is sort of customizable. You can choose how big they are. In fact, there you go. There's the size field just there. But the short answer is there is a blow up. Of course, it depends on how many analytics, how many sort of cubes you set up, but it's not as big as you might think. Okay, cool. I want to stop there and hand over to Nicolas, who's going to tell you about virtual nodes. Thanks.
Okay, welcome to this talk on virtual nodes, a feature that we call the operational aspirin for Cassandra. I'd like to start with a 1-minute recap on how Cassandra distributes data in a cluster. So Cassandra is a distributed database. It tries to spread your data set across multiple nodes. And the way that it does this is using a technique called consistent hashing. Nodes are clustered in a structure that we call the ring. So this is a picture that I will reuse in this talk. In this case, we have 4 nodes, each one having a quarter of the data set. So think of it as like a clock face in which you have between 0 and 3 o'clock, all the data goes to the yellow node, etc. So the way you configure this in Cassandra, at least before virtual nodes, is by giving a token to each node. So in this case, the blue node has token 0, the yellow node has token max token divided by 4, max token divided by 2, 3/4, etc. So if you have 10 nodes, you would take this maximum token, divide it by 10, and then give 0 times this to the first node, 1 times this to the second node, etc. This is something you have to do by hand when you set up your cluster. The way that Cassandra used to do it is using MD5, reduced to 127 bits instead of 128. Now it uses Murmur 3, which is 160 bits, I think. But it doesn't really matter which hash function it uses. The point is that this will distribute data all across the cluster evenly, as long as your partitions obviously are set up properly. If you set up one partition which is just between 0 and 1 o'clock, your 1 node out of 4 will only receive 1 key out of 12 only. Okay? So this has some limitations. In particular, the main problem is the operational complexity of the system. There are some problems in setting this up. It's quite error prone. We frequently see people getting this wrong and ending up with unbalanced clusters, which can cause problems. It's also a liability when you try to rebuild the cluster in the way that we'll see in a little bit. But the main point is that when you try to add a node or remove a node, you will not involve your whole cluster, but only a local fraction of it, which is not exactly what you would want from a peer-to-peer, masterless, decentralized distributed system. In terms of maintenance as well, there are some processes that you need to run in Cassandra, in particular something called repair, in which the nodes will synchronize themselves in a distributed fashion, and this involves, without virtual nodes, only in the same way a small fraction of the cluster. When you add or remove nodes, when any sort of topology changes happen, when you add a data center, this is a manual process, it's quite tedious, and this is not a modern way of distributing data. So let's take the example of adding a node to an existing cluster. We have this cluster of 4 nodes. It's balanced, right? We have 25% of the data on each node. And we want to add the 5th one to accommodate for growth, for more throughput, etc. So the way we would add it in the first place is to insert the new node in the cluster. This new node would come up at around 5 o'clock, let's say. This is a random pick. But if it comes at 5 o'clock, it only has a 12th of the whole ring, which is not what we want. We want all these nodes to have something like, well, to have 20% of the ring. So there is a manual process in which we need to move each node from their original token, let's say 0, 25%, 50, 75%, to 0, 20%, and 20, 40, etc. This process is manual. This is something you need to do per node. And as you can see, the data that was originally at, let's say at 6 o'clock, was on the green node, and now it's been transferred to the new node, right? So this involves data transfer in your cluster. If you do it node by node, you can see that it only involves the immediate neighbors of the new node in the ring. This is time consuming, it's resource intensive as well, and it's generally a pain to do, at least in small clusters. So what people tend to do is, at least for small clusters, is to double the number of nodes. You can see here that from 4 we moved to 8, which means that we only inserted a new node, let's say at 12.5%, which transferred some data from the yellow node to the orange node, but didn't need to do anything else really. This doesn't really scale when you're growing from more than 8 nodes, right? You can't really justify spending double the money every single time. Usually what people do above 8 or 10 nodes is to start a new data center. So they push this problem a little bit further in time, but it's still, in general, an operational pain. So the way to add or remove nodes is to insert this new node with a new token and rebalance those ranges. So ranges are these partitions, these slices of the whole data set that belong to a node or another. In general, this is something that people do wrong. Either they make mistakes in the calculation of their new tokens, or they will move more data than is optimal. Right? If you add a new node from 4 to 5, maybe you'll leave the one that's at 0 and you'll move the one that's at 25% to 20%. So you're moving 5% of your data to the new node to another one. But in general, you will not go through the most optimal process. So there are some commercial tools that will give you a rebalance option that will try to calculate the minimum amount of work for rebalancing, but if you do it by hand, you'll probably do it wrong at least a little bit. As I said, it only impacts the immediate neighbors of a node, so it only impacts replication factor nodes that are around the one that you're currently moving. If you have 100 nodes, or for some of our customers, 2,000 nodes, moving a few out of several thousands is not really the most efficient way of balancing of spreading the work among those nodes. It's all right. It's manual, tedious, error-prone, painful, and in general, it's now a thing of the past. Removing a node is a pain in the same way, and it is pretty much the same operation in reverse, in a way that people will, for small clusters, divide the number of nodes by 2, and removing one node will involve the same process except in reverse. When you have your 5 nodes with 20% each, if you remove one of them, you will have to rebalance all of the surviving ones to 25%. Right. So this is a limitation not just in terms of operational pain, but also in terms of scale. In a way that if you have a plan for the availability of your system, and if you plan for, let's say, at most a node being down for a whole day, for 24 hours, then having a limit in the amount of data that you can stream in one day means that you cannot really put more than, let's say, 1 or 2 terabytes of data per node. If you have 2 terabytes of data per node, rebuilding a whole node, replacing it or removing it or adding it will take about 24 hours of just streaming data into the system, because only the immediate neighbors are involved in this. The solution is then this new feature, called virtual nodes. Virtual nodes are newish in Cassandra 1.2. Cassandra 1.2 came out in December last year, so it's starting to be an established feature, and I recommend you definitely use it if you're not at the moment. The main point of this is to have more than one token per node, instead of having a single spot on the ring for which defines the range that you're responsible for, which includes all the data up to that token. You'll have more than one token per node. The way to do it is, if you have more than one token per node, if one token was difficult enough to set up, it will not be a manual process. It is, in this case, a random process. So each node will assign its own tokens at random. As we'll see, this actually leads to a balanced distribution of data, even though that might seem counterintuitive. The good features of virtual nodes is that they let you grow your cluster one node at a time instead of doubling the number of nodes. They remove this operational pain of having to recalculate tokens and having to manually set up your cluster that way. In the same way, removing nodes is supported with the same ease. Other good things, you're now streaming data when moving partitions. When adding or removing nodes, you're streaming data from all nodes instead of just the local replicas. The main downside, although it's not that consequential, is that only random partitions are supported now. Traditionally, Cassandra used to have 2 ways of distributing data, either using a hash-based partitioner called the random partitioner, or now the murmur-free partitioner, using this hash function that then dispatches data all over the place. Or you could have manual token assignment, in which you would say all the users with name from A to F would go to this node, from G to L would go to that node, etc. This was quite tedious and error-prone as well. That doesn't really work with virtual nodes, and it's not tested with virtual nodes. Okay? And multi-DC, multi-data center support just works in the same way now. So virtual nodes means having more than one token per node. There are different ways to do this. It means that now we're splitting the token space, the key space, into more than 4 partitions, into more than 4 ranges for 4 nodes. And there are different strategies. So the one that Cassandra 1.2 uses is to have, if you consider n the number of nodes and b the size of your data set, the number of partitions here would be proportional to the number of nodes. Typically in Cassandra 1.2 and over, you would have 256 partitions, 256 ranges per node. So in our 4-node cluster, that's 1,024 ranges that are spread all over the ring. It means that the partition size in this case grows in proportion of the data, but also is lowered by having an increased number of nodes. It's a bit different from the way that React distributes data. React has virtual nodes as well, but you have a fixed number of virtual nodes in the whole cluster, and this is defined when you install React. And MongoDB, although I'm certainly not an expert on Mongo, but I believe this is how it works with auto sharding, that you have a certain number of partitions which depend on the size of the data. I think that's the case also if you use HDFS, in which the partitions are really the HDFS blocks that are spread across your cluster. So virtual nodes are new in 1.2, and it's important to talk about them now because they are now enabled by default in version 2.0, which came out in September. The way to do it if you're starting a cluster today is to set num tokens to 256 in Cassandra.yaml. I say that it's not enabled by default in 2.0. This line exists in the config file. It's just commented out in Cassandra 1.2. So let's see how it works. When we start a single node, it will start with 256 tokens. Well, this one has about 10 or so. I said that these tokens are generated at random, so they split the ring into 256 ranges of various sizes. As you can see here, some of these ranges are larger than others, sometimes a lot larger than others. Adding a new node will also generate 256 new tokens and spread those across the cluster. So by injecting its own tokens into the ring, a new node will steal some data from the existing nodes. In this case, there's only one. So the one that joins will then start to own the ranges that are here represented in green. When we add a third node, it will also inject its own tokens into the ring and steal a little bit of data from the green node, steal a little bit from the red node, etc. You can see how adding more nodes to the cluster will lead to a more balanced version, a more balanced distribution in this case. So in practice, it is very close to 1 over n for all your nodes. It's true that it's not exactly that. It differs often by a few %, but really it's not a big deal. In practice, it doesn't really matter at all. An ideal distribution would be that all the nodes have ranges of equal size, completely spread across the cluster. Actually, it looks more like this, where you have ranges that are a lot larger than others. But the distribution of ranges is such that some nodes will have larger ranges, but it will balance out in the global picture. Adding a new node, so that's this process called Bootstrap, will then assign a host 256 tokens, split ranges from existing nodes, and it means that instead of having data sent just from the local neighbors, you have the new node steal data from all the existing nodes, and this will stream data in from your whole cluster. It will involve all your nodes in Bootstrap. Right, so what you get from this is, right, no need to rebalance. You just add one node to grow your cluster, and you could remove one node one at a time as well. So if we remove the one that has the blue ranges, we end up in the same situation as before. It will release some of the nodes some of the ranges that it stole from the green node to the green node, and same thing for the red node. Removing a node is now called node tool remove node, because remove token doesn't really make sense if you have more than one token per node. So nodes have now a host ID, which is just a randomly generated unique identifier. The tokens are all removed from the ring, and the data is released not just to the immediate neighbors, but to all the other nodes in the ring. So node tool ring, which is the first command you run in your cluster, becomes quite useless if you have 1,000 ranges to display. This is not something that will really be meaningful in your environment. It becomes replaced by node tool status, in which you can see this host ID, and you can see the columns called owns, which is the sum of all the sizes of the ranges that this node is responsible for over the size of the whole ring. So in this case, I just started 5 nodes at random. I didn't change anything in the configuration, just made sure that the virtual nodes were set up properly. And you can see that I've got pretty much an even distribution. I have one node as 21.3% of the data, but really that doesn't really matter at this stage. It also means that having heterogeneous hardware is now possible. If you have one node with 156 tokens and one with 128 tokens, the one with 128 will steal ranges that are still fewer ranges, so it will only have half the data as the other one. This was quite difficult to do with Cassandra 1.1 and before, because you had to have an unbalanced ring on purpose. You had to skew your tokens so that a node would have 12% instead of 25%, but well, it looked wrong on the whole picture. Okay, some math. We ran some simulation on what it means to have random ranges. So this is just running simulated token assignment. If you pick, let's say, 10 nodes and you give them 1,000 tokens each, you just insert them at random in this token space, and you look at the distribution of range sizes. And you can see that well, there are some ranges that are much larger than others, and some ranges are much smaller than others. But this is a distribution that applies not on the whole, it applies on the whole cluster, but all the nodes have the same distribution of some large ranges and some small ranges. This is what, this is where this distribution, this even distribution comes from. Not that there is a skew in the distribution of range sizes themselves, but that all nodes have the same distribution. Right. So we ran the test in simulating data insert into this cluster, and this is roughly what we got. You can see that on the x-axis you have the virtual node location. That's really the token itself, between 0 and 1 billion, let's say, in this, if that was your token space. And on the y-axis you have the amount of data stored per node, and as you can see, some of them are much larger than others. In practice, this is something you would see if you were to represent all the tokens in a ring fashion. Right? You would see that some of them are really close to each other and some of them are quite far apart. When you put this together in the whole cluster, you end up with a distribution which is very much centered, which is very much a normal distribution centered on the expected amount of data that you would have for n ranges in that space. So you have an nth is centered on one n, n being the total number of virtual nodes, or total number of tokens in the ring. So in this balanced cluster, we now have keys that are randomly distributed, evenly distributed in the cluster by the random partitioner, and in practice it does tend to balance itself out. So I ran the test just before this talk. Started 2 nodes. They started with 48 and 51%. 3 nodes, about almost a third. 4 nodes, almost exactly 25%. In practice, if you have 60 nodes, they will be completely equal. We also did some performance testing to validate these claims of faster bootstrap and decommission. We started a 17-node cluster on EC2, inserted almost 500 million keys into that, and timed how long it took to remove a node or to add a new one. Sorry, to remove a node and then to add it back. Removing a node took about a third of the time. Well, it's not exactly 17 times faster, but you can see that it's a massive improvement. And bootstrapping was quite a lot faster as well. It doesn't sound that impressive now. Keep in mind that this was about a year ago. There have been quite a lot of improvements in the streaming protocol of Cassandra. I would expect this to be much better now. So virtual nodes are great. How do you use them if you have an existing cluster? This is kind of the pain point of virtual nodes. There are different ways that you can migrate an existing cluster to virtual nodes. The simplest way is just to start a new cluster, inject your data into it, and then destroy your old cluster. If you're running in a virtualized, in a cloud environment, that's something that's easy to do, but you'll have some downtime because you're effectively restoring from backup. If you want to do it without downtime, you can create a new data center. So that would be twice the hardware, and start to replicate the data into the new data center. And when this is done, destroy the old DC. You need then, in this case, twice the hardware. That might be possible depending on your case. There is an official way of migrating to a vnode cluster, which is called Shuffle. Shuffle is a utility which is bundled with Cassandra. The way it works is you would stop one node at a time and then start it again with virtual nodes enabled. So if you think of your 4 nodes in this equally divided quadrant of 25% each, if you stopped one node, then enable virtual nodes there and then started it again, what Cassandra will do is identify that there was a running Cassandra cluster, Cassandra node there with 25% of the data. It will take this range and split it into 206 tokens. These will be consecutive and divide this quarter of the ring into partitions of various sizes. You do this for one node at a time for all your nodes, and you end up with a cluster with virtual nodes in which you're not really distributing all this data. You still have, the point about virtual nodes is that you're supposed to have all this mix of partitions together. So the way that Shuffle works is that it will take 2 partitions and then swap them. Say, okay, now you're responsible for this and you give me the other partition. And it will do this quite a few times until the data is sufficiently shuffled together and you have effectively a mix of virtual nodes everywhere. I don't think I've ever seen anyone use Shuffle successfully. Have you?
Yes.
Well, you're the one. So Eric, who used to work at Acunu and who wrote Shuffle, said that it worked on his laptop. That was the only guarantee we had so far. So okay, I'm glad to hear that someone managed, but it is quite broken, I would say. So the recommended ways would be, well, to provision more hardware and add nodes like this. Yeah. So you should really be using virtual nodes by now. If you haven't, then there is a migration path. It is worth it because managing tokens and shuffling data together, moving data together by hand is really a pain. And this will let you grow your cluster and manage Cassandra in a much easier way. Right? Thank you.